Welcome to the specialization on Generative Adversarial Networks, or GANs for short. You'll see how to build models that can generate realistic images, music, and other things. In this video, you're going to gain some intuition about how GANs and their family of models work. And by the end of the week, you get to build your own GAN that generates handwritten digits. In this video, I'll introduce you to what generative models are, of which GANs are a type, and how these models compare with other models that you might already know about. And I'll also talk about two of the most popular generative model architectures. You may be familiar with discriminative models, but you might not have known how they fit into the larger context of machine learning, or ML. A discriminative model is one typically used for classification in machine learning. They learn how to distinguish between classes such as dogs and cats, and are often called classifiers. Discriminative models take a set of features X, such as having a wet nose or whether it purrs, and from these features determine a category Y of whether the image is of a dog or a cat. In other words, they try to model the probability of class Y, given a set of features X as having a wet nose but it doesn't purr, so it's probably a dog. On the other hand, generative models try to learn how to make a realistic representation of some class. For instance, a realistic picture of a dog you see here. They take some random input represented by the noise here, which could take on the value, let's say 3, a random number, or -5, or 2.6, or actually just a vector of all of those values. The point is, the noise represents a random set of values going into the generative model. The generative model also sometimes takes in a class Y, such as a dog. And from these inputs, its goal is to generate a set of features X that look like a realistic dog. So an image of a dog with features such as a wet nose or a tongue sticking out. So you might wonder why we need this noise in the first place. Why can't we just tell it, hey, generate a dog for me, and then it'll generate a dog? The noise largely here is to ensure that what's generated isn't actually the same dog each time. And you'll see this theme play out shortly. And this is because generating just one dog is no fun and also a little pointless. So for now, think of this as some random noise that also goes in as an input. All right, so more generally, generative models try to capture the probability distribution of X, the different features of having a wet nose, a tongue sticking out, maybe pointy ears sometimes, but not all the time, given that class Y of a dog. And with the added noise, these models would generate realistic and diverse representations of this class Y. And actually, if you're only generating one class, one Y of a dog, then you probably don't need this conditioning on Y, and instead it's just a probability over all the features X. And you can see from the side-by-side comparison that the discriminative models and the generative models actually mirror each other a bit here. All right, so as an example for a generative model, in a good run of a generative model, you could get a picture of this pecking geese, and in another run, a Tibetan Mastiff. And if you continue to run it multiple times without any restrictions, you'll end up getting more pictures representing the dataset your generative model was trained on. And that might look like a lot of cute Labrador retrievers. There are many types of generative models, and I'll briefly introduce you to the most popular ones: variational autoencoders, or VAE for short, and GANs. VAEs work with two models, an encoder and a decoder, and these are typically neural networks. They learned first by feeding in realistic images into the encoder, such as this really realistic image of a dog that I drew. Then the encoder's job is to find a good way of representing that image in this wonky latent space. Let's say it finds a place right here. And let's say this point in the latent space can be represented by this vector of numbers, 6.2, -3, 21. And what the VAE does now is take this latent representation, or a point close to it, and put it through the decoder. And the goal of the decoder is to reconstruct the realistic image that the encoder saw before. So that's assuming the decoder has already been trained to be pretty good. But in the beginning, the decoder won't be able to reconstruct the image, and maybe the dog produced will have evil eyes. Now, after training, we actually lop off the encoder, and we can pick random points in the latent space, such as here, and the decoder Even though they've only been around since 2014, GANs have already achieved super impressive performance across a multitude of tasks. And if you haven't seen some of their results, you're in for a treat. So in this video, I'll show you some cool applications of GANs, like the generation of realistic human faces and the animation of famous artworks. Then you'll get to see some of the amazing projects major companies are using them for. This tweet is from Ian Goodfellow, who is widely regarded as the creator of GANs, and it shows a striking visualization of the rate at which GANs have improved over the years. You can see how GANs have progressed from black and white and rather inhuman-looking faces in 2014 to much higher quality, colored, photorealistic faces in 2018, and they've been getting actually even better up until this day. So case in point, progress has only increased since then. In early 2020, NVIDIA released a GAN that could generate images like these, which are so high resolution and look like professional photographs. And they have a soft background effect and everything. So it's easy to think that these people are real, but they actually don't exist. Amazing, isn't it? GANs can learn from whatever training data they're given, so they're not limited to reproducing human faces. And here's the model, the same one from before, but this time producing cats. And so if you look closely, you can see some really weird looking images because not every generated example is perfect in this case. There's some semblance of a cat going on here, but of course I have no idea what that is. And also something that's pretty cool is that you can actually observe images with text on them. And this happens because, as mentioned before, generative models try to mimic the distribution of the data you're using to train them on. In this case, the training data was scraped from the web of all of these cats, and this includes a lot of cat memes with meme text on them. What's funny, of course, is that this meme text on the generated cat memes don't actually make up words because the generative model is not trying to model words, but rather the visual realistic effect. And that being said, some of these are actually pretty cute and realistic, even though they might not be ready for Reddit just yet. GANs can also perform image translation, which just means they can take an image from one domain and transform it into another. For instance, they can transform an image of a horse into a zebra and vice versa. What's really, really interesting is that you don't actually need examples of a zebra and a horse doing the same things, and instead just transfer that style over. In the same way, GANs can help you draw. This model can take a rough drawing of a landscape and make it photorealistic. So you can have brushstrokes here on the left. This is a person putting really rough brushstrokes together of different classes, such as a cloud or a mountain or a lake. And then the GAN from this really rough sketch is able to produce something really photorealistic. So in this GIF, a person is able to make rough sketches with just a few lines and color, and then the GAN can transform them into realistic pictures. A GAN can also take a still life portrait, for example, the Mona Lisa, and animate it using the motion of any real person's face. So they don't even have to look like the Mona Lisa to play the part. And if you're reminded of the talking portraits at Hogwarts, you're not alone. In a sense, GANs are magic. And GANs don't stop at 2D images. They can also generate 3D objects like chairs and tables. And these can be applied to fields like generative design, where you can create cool furniture for your house. There are also diverse applications in medicine, where you can use your GAN for generating artificial medical data or even detecting abnormalities in x-rays. You'll get to see more on this in course 3, but showing all the cool applications out there could take hours. Several prominent companies have also started using generative adversarial networks for a variety of applications. For instance, Adobe is thinking about the next generation of Photoshop, where novice artists can perform at an expert level, for example, with those doodles. Google is using them for text generation largely, but also with images. IBM is using GANs for data augmentation, so using a GAN to generate synthetic examples to augment the data set for a classifier downstream. For example, if you don't have enough data of a certain class or of a certain type of image. Snapchat and TikTok put them to work in creative new filters, which you've probably seen and used. And even Disney is using them for super resolution. So at the end of the specialization, you'll be able to use GANs as well for whatever application you like. All right, so in summary, you saw the rapid advancements that GANs are powerful models that learn to produce realistic objects that are difficult to distinguish from existing real ones, for instance, human faces. A GAN learns by making a generator and a discriminator compete against each other. In this video, I'm going to talk about the goals of the generator and the discriminator. And you'll see how the game between them begins and how that really plays out as they one-up each other until we get a generator that is really, really good and can produce realistic images that you want. So recall that GANs have two components. One's called the generator and the other is called the discriminator. And these are typically two different neural networks. The generator learns to generate fakes that look real to fool the discriminator, and the discriminator learns to distinguish between what's real and what's fake. So you can think of the generator as a painting forger and the discriminator as an art inspector. So the generator forges fake images to try to look as realistic as possible. And it does this in the hopes of fooling the discriminator. So you can see here Starry Night and Scream. They look pretty good. Meanwhile, the discriminator here looks through a pile of both real famous paintings and the fake ones created by the generator and tries to tell which ones are real and which ones are fake. So here the ones bordered with that pink purplish color are fake and the ones that are bordered with green are real. And as you can see a bit from this setup, in order to fool the discriminator, the generator will try to forge paintings that look more like the real ones. And in order to catch the generator, the discriminator will try to learn how to not get fooled, even by the closest replicas. So to start this game, all you need is a collection of these real images, like some famous paintings, if you want the generator to paint famous paintings. And so at the beginning of this game, the generator actually isn't very sophisticated. It doesn't know how to produce real-looking artwork. So I'm going to represent the generator as this meme of a dog trying to paint. Additionally, the generator isn't allowed to see the real images. It doesn't know how this painting should even look. So this is really, really tough for the generator, especially in the beginning. So at the very beginning, the elementary generator initially just paints a masterpiece of scribbles. And don't judge her. Nobody ever told her what to do and what to generate here. And so your other beginning component is actually an elementary discriminator that doesn't know for sure what's real and what's fake. And represented here as a dog with a beret on, trying to be an art critic here. But in this case, he's allowed to look at the real artwork. It's just jumbled up with the fake ones as well. And he doesn't know which one is which. That's for him to figure out and learn how to decide. So to start the competition, you train the discriminator using the real artwork so it's able to know which images are actually real. So after it decides, maybe this looks real, you actually tell it, yes, that's real, or no, that's fake. This way, you can get a discriminator that's able to differentiate a poorly drawn image like this from the ones that are slightly better, and eventually also the real ones. Of course, the discriminator gets these all jumbled up, so it doesn't know up front which ones are real, which ones are fake, but you do tell it as it learns which ones are real and which ones are fake, whether it's right or wrong in determining those two classes. And when the generator produces a batch of paintings, the generator will know in what direction to go on and improve by looking at the scores assigned to her work by the discriminator. So this one looks a little bit more real, so maybe the generator here will start painting a little bit more realistically, towards a face of maybe the Mona Lisa. Not quite there yet, but almost. And the discriminator also improves over time because it receives more and more realistic images at each round from the generator. And it always, remember, receives both real and fake images, all jumbled up in a pile. But essentially, it tries to develop a keener and keener eye as these images get better. And so when it says that this image here, created by the generator, is 60% real, you actually tell it after it says it's 60% real, that it's wrong, that it's not necessarily real, that it's actually fake. And then after many rounds, the generator will start producing paintings that are harder and harder to distinguish, if not impossible for the discriminator to distinguish from the real ones. And then at this point, when you, the person who wants a good generator to generate awesome fake images, when you are happy with the result of this generator, the game will end. So in summary from this lesson, it's important to take away that the goal of the generator is to produce fakes that look real to the So GANs are composed of two models, the discriminator and the generator. In this video, I'll show you first how the discriminator works. The discriminator is a type of classifier. So I'll start with a refresher on what that is. Then you'll see in probabilistic terms what classifiers learn to model. And at the end of this video, I'll show you how it all translates to the GANs discriminator. So as a quick recap, the goal of a classifier is to distinguish between different classes. So given this image of a cat, the classifier should be able to tell that it's a cat and not a dog, for example. In fact, it can learn to differentiate cats from multiple different classes, and this depends on which classes you want it to differentiate. Probably the simplest case is probably just cat and not cat. Classifiers aren't limited to determining image classes, so you could have this piece of text right here, it meows and plays with yarn, to classify into a cat. You could have a video of a cat purring, all sorts of different things here. So one type of model for a classifier is using a neural network, and this neural network can take in some features X. For example, here there's X0, X1, X2, all the way up to Xn, so n different features. It computes a series of nonlinearities, which I'll get into later, and outputs the probabilities for a set of categories.
And it thinks that it's 45% likelihood of this image being a cat, 45% likelihood of this image being a dog, and 10% likelihood of this image being a bird.
And in the beginning, the model probably won't know how to classify correctly, so that's why cat and dog are probably on par with each other here, and it learns over time trying to improve its predictions according to the true labels from the data. So you'll tell it at the end, no, this is 100% cat, 0% dog, 0% bird. So this learning process can be summarized as follows. You have some input features X, such as that it purrs and it likes to play with yarn, and a set of labels Y's associated with each of your classes. For example, a cat, a dog, and a bird. And you use your neural network, which takes in those features and learns these set of parameters, which I'll call theta. And these are each of those nodes you see in that neural network. And these weights change over time as it learns what a cat looks like, and what a dog looks like, and what a bird looks like. And these parameters, theta, are trying to map these features X to those labels Y. And those predictions you'll call Y hat, because they're not exactly the exact Y labels. They're trying to be the Y labels. And so the goal is to reach a point where the difference between the true values Y and the predictions Y hat is minimized. And this is where a cost function comes in, and it's computed by comparing how closely Y hat is to Y. And that's the goal of this cost function, which tells this discriminative model, this neural network, how close it is to classifying cat correctly, and dog correctly, and bird correctly. So from this cost function, you can update those parameters, those nodes in that neural network, according to the gradient of this cost function. And that just means generally which direction those parameters should go to try to get to the right answer, to try to get to a Y hat that's as close as possible to Y. And then you repeat this process until your classifier is in good shape. So let's take a little ride into math land, where the goal of the discriminator is to model the probability of each class. For example, not just cat here, but turtle, bird, dog, and fish as well. Given a set of input features, for example, here's an image of a cat. So given this image of a cat, which class is this? In other words, this is modeling the probability of class Y given input features X. And again, these features could be features extracted from this image, such as that it purrs and that it likes to play with yarn, but also the pixels themselves. And this is a conditional probability distribution because it's predicting the probability of class Y conditioned on a certain set of features, which is what this vertical bar is for. So the model only makes a prediction of a class once it's seen the input features. And in this case, it's an image. And now bringing it back to the GAN context, the discriminator is a classifier that inspects the examples, the fake examples, the real examples, and determines whether they belong to the real or fake class. So taking in this fake Mona Lisa here, and instead of determining whether there is a cat, dog, or bird in this image, determining how fake this image is. And here it thinks it's 85% fake. In probabilistic terms, the discriminator models the probability of an example being fake given a set of inputs X. For instance, it'll look at this picture of a fake Mona Lisa and determine that with 85% probability, it isn't the real one. And as a simplification, it'll be classified as fake. And you can also think of this as 0.15 real The generator in a GAN is like its heart. It's the model that's used to generate examples and the one that you should be invested in helping achieve a really high performance at the end of the training process. In this video, I'll revisit the role of the generator and you'll see how it's able to improve its performance. Then I'll show you what it models in terms of probability. So the generator's final goal is to be able to produce examples from a certain class. So if you trained it from the class of a cat, then the generator will do some computations and output a representation of a cat that looks real. So ideally, the generator won't output the same cat at every run. And so to ensure it's able to produce different examples every single time, you actually will input different sets of random values, also known as a noise vector. And so here, this noise vector is actually just a set of values where these differently shaded cells are just different values. So you can think of this as 1, 2, 5, 1.5, 5, 5, 2. And then this noise vector is fed in as input, sometimes with that class Y for cat, into the generator's neural network. So this means that these features x0, x1, x2, all the way up to xn include the class as well as the numbers in this noise vector. And so then the generator in this neural network will compute a series of nonlinearities from those inputs and return some variables that look like a cute brown and white cat in a run. So here, instead of different classes, its output will actually be an image. And so you can imagine maybe this image has 3 million pixels. So you can imagine those being 3 million nodes at the end there that do not necessarily represent classes, but each pixel's value. And in another run, it can generate this Sphinx cat, and maybe in a final run, this Savannah cat. And these are all with a different noise vectors. So let's first consider conceptually how the generator improves over time. First, you have a noise vector, or those random input values you saw, which I'm going to represent with this Greek symbol here of psi. And you pass this into a generator represented by a neural network to produce a set of features that compose an image of a cat or an attempt at a cat. For example, your generator might generate this. And this image x hat is fed into the discriminator, which determines how real and how fake it thinks it is based on its inspection of it. And after that, from what the discriminator thinks of it, which is this y hat with a d here representing that it's the discriminator's predictions, you can compute a cost function that basically looks at how far the examples produced by the generator are being considered real by the discriminator, because the generator wants this to seem as real as possible. And so basically, the generator wants y hat to be as close to 1, meaning real, as possible, whereas the discriminator is trying to get this to be 0, fake. And it uses the difference between these two to then update the parameters of the generator. And that gets it to improve over time and know which direction to move its parameters to generate something that looks more real and will fool the discriminator. So once you get a generator that looks pretty good, you can save the parameters theta of the generator. And that typically means freezing those theta values and saving it somewhere. And then you can load it back up and then sample from this saved generator. And what sampling basically means is you have these random noise vectors. And when you input that into the saved generator, it can generate all sorts of different examples. And so this saved generator was not trained on cats, I hope, because it's generating dogs. Note that you can continue generating new noise vectors, putting it through this saved generator, and then sampling more dog images in this case. So in the land of probability, the generator models the probability of an example, such as a cat. In the previous example, it actually was a dog. And of course, you can do one of a turtle, bird, or fish as well. Please go crazy with that. And more generally, the generator is trying to model the probability of these features of a cat, such as licking its paw, or having cute whiskers, or having different types of fur, given this class Y of a cat. So this is the conditional probability of features X given the class Y. However, since we only have one class at the moment for, let's say, just generating cats, then Y will always be the same. And so you don't actually need this here, so that you have P of X that you're modeling. Of course, if you want your generator to learn across all different types of classes and you care about the class, then you do need to put that class. The binary cross entropy function, or BCE for short, is used for training GANs. And it's useful for these models because it's especially designed for classification tasks where there are two categories, like real and fake. In this video, I'll show you the equation used to get the BCE loss and what every part of the equation means. At the end, I'll wrap up this lesson by showing you how the BCE cost function looks for different labels. All right, so here is the full BCE cost function. It might look a little bit intimidating, but I'll break down each of these components and also give you examples to provide some intuition on how it works. So first, at the beginning here, you see a summation sign from 1 to m, as well as dividing by that m. And so this basically just means summing over the variable m, which is actually the number of examples in the entire batch, and taking the average of those examples, taking the average cost across this mini batch. And I'll go over what this negative sign means later on. So throughout this video, H denotes the predictions made by the model. So you see that here. Y is the labels for the different examples. So these are the true labels of whether something is real or fake. For example, real could be a label of 1 and fake could be a label of 0. X are the features that are passed in through the prediction. So this could be an image. And theta are the parameters of whatever is computing that prediction. So in this case, it's probably going to be the discriminator. So it's the parameters of the discriminator looking at those features, and that's doing this h of x comma theta. Often you'll see this also written as h of x semicolon theta, and that just means parameterized by theta. And that's slightly more accurate, but you don't have to worry about that now. In these brackets, you can break these down into two different terms. And so let's look at each of them. So the term on the left is the product of the true label y times the log of the prediction, which is h of x, the features, parameterized by theta for the model. So to understand what this value is trying to get at, let's look at some examples. So the case where the label is 0, so let's say this means it's fake, and you have any prediction here, then this value actually results in 0. And if you have a prediction of 1 that's real, and you have a really high prediction that is close to 1 of 0.99, then you also get a value that's close to 0. And in the case where it actually is real, but your prediction is terrible and it's 0, so far from 1, so you think it's fake, but it's actually real, then this value is extremely large. And this is largely caused by the log there. And so what this is trying to say is that in the case when the true prediction is 0, this term doesn't matter, it just goes to 0. So this term is mainly for when the prediction is actually just 1, and it makes it 0 if your prediction is good, and it makes it negative infinity if your prediction is bad. So now looking at the second term, it looks very, very similar, save some of these minus signs in here. And so in this case, if your label is 1, then 1 minus y is equal to 0. And actually, if your prediction is anything, this will evaluate to 0. If it's fake, and if your prediction is saying, hey, that's pretty fake, it's close to 0, then this value is close to 0. If it's fake, but your prediction is really far off and thinks it's real, then this term evaluates to negative infinity. So basically, each of these terms evaluates to negative infinity if for their relevant label, the prediction is really bad. And so that brings us to this negative sign a little bit. So if either of these values evaluates to something really, really big in the negative direction, this negative sign is crucial to making sure that that is a positive number and positive infinity, because for a cost function, what you typically want is a high value being bad, and your neural network is trying to reduce this value as much as possible. So getting predictions that are closer, evaluating to 0, makes sense here because you want to minimize your cost function as you learn. So in summary, one term in the cost function is relevant when the label is 0, the other one is relevant when it's 1, and in either case, the logarithm of a value between 1 and 0 is calculated, which returns that negative result, and that's why you want this negative term at the beginning to make sure that this is high or greater than or equal to 0. All right, now I'll show you what the loss function looks like for each of the labels over all possible predictions. So in this plot, you can have your prediction value on the x-axis. So you've seen all the basics and the intuition behind GANs and their components. In this video, you'll review some previous concepts that I covered, as well as putting it all together so you can get started with training your GAN. So first, I'll share a representation of what a GAN architecture might look like, and then I'll show you how to train a GAN by alternating the training of the discriminator with the training of the generator. So recall that in a basic GAN, the generator takes a random noise as input with this psi Greek letter, and this generator then produces fake examples called x hat. And these are fake images, for example. And I don't need to pass a class to the generator, but I can if I'm generating lots of different classes. For now, I'm not going to pass a class to the generator. I'll show you how this works later. And then the generated examples, along with some real examples, are passed to the discriminator. And this probability, this output from the discriminator, is called y hat. And so the goal of the discriminator is to distinguish between the generated examples and the real examples, while the goal of the generator is to fool the discriminator by producing fake examples that look as real as possible. So to train a basic GAN, you alternate the training of the generator and the discriminator. So let's first start with how the discriminator works. So first, of course, you get some fake examples x hat produced by the generator from that input noise. And then those examples, the fake ones x hat and real ones x, are both passed into the discriminator without telling the discriminator just yet which ones are real and which ones are fake. And then the discriminator makes predictions, y hat, of which ones are real and which ones are fake, or more specifically, a probability, a score of how fake and how real each of these images are. After that, the predictions are compared using that BCE loss with the desired labels for fake and real. And that helps update its parameters, or theta d, where d represents parameters for the discriminator. And so this only updates the parameters of the discriminator, only this one neural network, and not the generator. All right, so for the generator, it first generates a few fake examples again, x hat, and this is from the input noise. And then these are again passed into the discriminator. But in this case, the generator only sees its own fake examples. It doesn't see the real examples at all. So it only knows that these are being passed to some discriminator. And then the discriminator makes predictions y hat of how real or fake these are. And after that, the predictions are compared using the BCE loss with all the labels equal to real, because the generator is trying to get these fake images to be equal to real, or a label of 1, as closely as possible. And so this is where it's a little bit tricky and a little bit different between the generator and discriminator. Discriminator wants the fake examples to seem as fake as possible, but the generator wants fake examples to seem as real as possible. That is, it wants to fool the discriminator. And so after computing the cost, the gradient is then propagated backwards and the parameters of the generator, or theta sub g, are updated. And note again, now it's only the generator, this one neural network, that is getting updated in this process, not the discriminator. So as you alternate their training, only one model is trained at a time while the other one is held constant. So when training GANs in this alternating fashion, it's important to keep in mind that both models should improve together and should be kept at similar skill levels from the beginning of training. And so the reasoning behind this is if you had a discriminator that is superior than the generator, like super, super good, you'll get predictions from it telling you that all the fake examples are 100% fake. Well, that's not useful for the generator. The generator doesn't know how to improve. Everything just looks super fake. There isn't anything telling it to know which direction to go in, maybe to, add something a little bit more realistic and how to learn over time. Meanwhile, if you had a superior generator that completely outscales the discriminator, you'll get predictions telling you that all the generated images are 100% real. So when training GANs in this alternating fashion, it's important to keep in mind that both models should improve together and should be kept at similar skill levels from the beginning of training. And the reasoning behind this is largely because of the discriminator. The discriminator has a much easier task. It's just trying to figure out which ones are real, which ones are fake, as opposed to model the entire space of what a class could look like, what all cats could look like. And so the discriminator's job is much easier than the generator's. One common issue is having a superior discriminator, having this discriminator learn too quickly. And when it learns too quickly, it suddenly looks at a fake image and says, this is 100%